Okay, so we'll go ahead and get started with this next section of notes here. Today's notes are going to be 8.2, triangle similarity, and the date that we did this is going to be the 4th of March. Our objective for today is we're still kind of talking about similarity and using these ideas with proportional sides and congruent angles. But specifically today, we want to make sure we are able to prove, or in other words, show that triangles or that figures are similar, and specifically we're going to be doing that with triangles today. So there will be no proofs with this, but we want to be able to show why we could set up these equations, or why we could say that the figures are similar. Because up to this point, every other problem we've done, they've just told us from the start that the figures are similar. So first theorem with this today is going to be the AA similarity theorem, or in other words, the angle-angle similarity theorem. And simply put, it just says this. It says if two angles of one triangle are congruent to two angles of another triangle, so if I look and I see two angles of one triangle are congruent to two angles of another triangle, then what I can say is then the triangles are similar. So remember, we're not talking about congruence anymore, we're just talking about similarity. So in other words, same shape but different size. And specifically in this one, it's saying that if I just see two angles that are congruent, then I can say that those shapes at least have to be similar. So for example here, obviously there's many different ways we could draw this here. Let's go ahead and just draw two triangles. Okay. And we'll keep it simple. Let's just say we have an angle of 100 degrees and an angle of 30 degrees. Same thing over here. Angle of 100, angle of 30. What this theorem is telling us is it's saying if we saw this, then we could say that these triangles are congruent here. And the reason for that is because we know similar shapes should have all congruent angles. Okay, the sides are going to be different, but the angles are all going to be the same. Well, notice here, if these are two triangles, I know all of the angles in a triangle have to add up to 180. So if I have two of them that add up to 130 in this instance, and two of them in another shape that add up to 130, I know that last pair of angles also has to be congruent, which means at the very least, the shapes are going to be the same shape, or at least similar. Okay, so with that here, let's practice that and make sure we understand how we can put that to use in some different problems here. Okay, so example one, if you'd like to, you can pause your video and sketch these here. And it's saying for each pair of triangles, I want to determine if they're similar and then just explain how I would know or how I don't. So no values to find here, no solving for a variable or anything like that. So if I'm looking at this first pair of triangles, I see these are right triangles. I have an angle of 90 in each of them. And then I notice one is 44 degrees and one angle I'm given is 47 degrees. So just on the surface, just by looking at it, I see that those angles aren't the same, so this doesn't match our theorem. But a good thing that I need to make sure to double check is, would these angles be congruent? Or in other words, I need to find the third angle of each of them just to double check and make sure that doesn't match up anything in the other triangle. So in this case, if one angle is 90, the other is 44, that last angle in that triangle is going to be 46. And then same thing over here, just double checking. If one angle is 90 and one angle is 47, that last angle is going to be 43 degrees. Okay, so I see that there's there's not two pairs of angles, I only see one pair of angles. So since that is the case, I'm going to say no, not enough congruent angles. I only have one pair. For our similarity theorem, we need two pair. Okay, not enough congruent angles. Okay, all right, and then the second one here, we have this diagram, and this is similar to something we saw back in Unit 6 when we were dealing with congruent triangles. If I see this here, I have parallel lines, and remember we talked about this, that means I can always look for alternate interior angles in this picture. So in this case, I know angle R would be congruent to angle W, because those are alternate interior angles, and then I also see angle X would be congruent to angle T as well for that exact same reason. So since this is the case, I do have a pair or two pairs of angles that are congruent, so I can say yes, these are similar by the angle-angle theorem. Okay, and then some of you might have been noticing as well, if we're looking at that diagram, there's also vertical angles in the middle. That's another pair of angles. So in this case, technically we had all three pairs of angles. Okay. All right. So now putting that to use, can we use that to solve for some different lengths here? So if I'm looking at this, I want to give the two pairs of angles that prove the triangles are similar by the angle-angle theorem, and then I want to use proportions to find x. Okay, so first off here, what are those two angles that I know are congruent? Well, I see a couple that are already marked for me, angle J and angle P. So I'm going to say angle J is congruent to angle P. Let's change that, angle P. Okay, first part done. And then the question is, what is the other pair of angles? Because obviously we need two if we're going to use this theorem. And again, we can see that idea I kind of just mentioned on the last one. Remember, we have vertical angles here in the middle. Anytime there's two intersecting lines, the angles across from each other are going to be vertical angles, or in other words, are going to be congruent. So I just need to make sure I name them correctly. So I'm going to say angle JLK. Make sure I order this correct. I want that middle letter to be my vertex. Is congruent to angle PLM. Okay, so these are the two angles that I have here. Angle J is congruent to angle P, and then JLK is congruent to PLM. And the good news is I don't need the third pair of angles because this is enough for the similarity theorem. So now I know these are similar, and now I can start to set up my different proportions here to solve for x. And remember, if we're setting those up, I can use the scale factor, and I'm looking for two corresponding sides that are the same number here. Or I'm sorry, not the same number, but they are numbers. They're not variables. So in this case, I see this here. I have 4, and I'm going to set that over 6. So 4 in the top shape, 6 in the bottom shape. And then same idea here with my other corresponding sides. I have a side length of x and a side length of 12. If I wanted to, I could reduce or simplify 4 over 6. But to keep it simple for us, we'll just say we can just set this as x over 12. Because either way, it's just going to give us the same answer. Okay, and then from here, there's multiple ways to solve. We've talked about cross multiplication. That's one way you can use, or you can solve for proportion here. But in this case, it's actually simpler to do one of those other things that we talked about, where I can just look and see, to go from 6 to 12, I would need to multiply by 2. And so it's the same idea on top. To get to x, x is just going to equal 4 times 2, which is 8. Okay, so simple enough. If we see proportions like that where they can just be solved very quickly and I can tell what you need to multiply one side to get to the other, feel free to do so. Otherwise, you want to make sure you're using cross multiplication. Okay, but either way, x is going to equal 8 here. Okay, so that's one theorem that we have that we can use in ways that we can use proportions. And like I said, we're going to see proportions a lot in this chapter. Okay, one other, or I should say a couple other theorems that we're going to see as well that we have is the side-side-side similarity theorem and the side-angle-side similarity theorem. Okay, so the side-side-side similarity theorem says this. It says if all three sides in one triangle, are, and at this point we're used to saying that they're congruent because we talked about congruent triangles and side-side-side, but with similarity we're not going to say they're congruent, we are going to say they are proportional. So I'm going to say if all three sides in one triangle are proportional to all three sides in another triangle, then what can I say? I'm going to say that same conclusion that we had before. I'm going to say then the triangles have to be similar or are similar. Okay, so this is just using that other property that we mentioned when we talked about similar shapes. As we said, the angles are congruent, and then this piece, the sides are proportional. So if I have the sides piece, that is enough to say that those are going to be similar. Okay, so for example here, we could obviously draw many different types of triangles here. We'll keep it simple. Let's say we have a triangle of 2, 3, and 4. And then we'll make another one here. This will obviously not be drawn to scale. But if I say I have one triangle with 2, 3, and 4, remember I just want the other sides, or the sides in the other triangle, to be proportional. So for instance, we could just say let's have a scale factor of 2. So we're just going to multiply everything by 2. This would become 4, this would become 6, and this would become 8. Okay, and that would be enough to say that those triangles are similar. Okay, so that's all I'm really looking for. And then once I have that, then I can use that to solve for different variables and different measurements. Okay, so that's side, side, side. And then the other one that we have, similar to that, is side, angle, side. Okay, and it's kind of like you would guess. I'm going to write this down here. I'm going to say if two sides of one triangle are proportional. Okay, if two sides of one triangle are proportional to two sides of another triangle. Okay, and then I'm going to add in one more thing here because we're forgetting the angle piece. So if I have two sides and two sides that are proportional and what we're going to call the included angle and the included angles are congruent. Okay, now that I have both those pieces, now I could say, or then I could say the triangles are similar. Triangles are similar. So kind of like we saw with side, angle, side when we were dealing with congruence, it's the same notion or same thought here, just a different way of using it. In this case, the sides don't have to be congruent, they have to be proportional. Angles still have to be congruent though. So for example, one way that we could see this, obviously we have many different ways to look at this here. You have a couple of triangles, let's say these are isosceles, let's say this is 4, 4, and then one congruent angle. And then the other triangle, I would need the same kind of thing, okay, except the sides are just going to have to be proportional. So for instance, let's say they're both 6 and 6, and then again, angle in between them would have to be congruent. Okay, and this would be an example of the side, angle, side similarity theorem. Okay, so we can use these, we can look for these because then this tells us, okay, now that I have this information, I can start to set up my proportions and solve for whatever I'm looking for. Okay, so example 3 here, saying using all the similarity theorems, I want to tell whether this pair of triangles are similar, and then if so, I want to give the similarity statement. Okay, so if I'm looking for this here, if we're thinking of the few different similarity theorems that we have, we know it can't be side, side, side because I don't have all three pairs of sides. We know it can't be angle, angle because I don't have any of the pairs of angles. So the only one that leaves is side, angle, side here. Okay, and I notice I do have, again, vertical angles, so I do have one pair of angles that are congruent. And then first, for this to be side, angle, side, I need those pairs of sides to be proportional here. Well, if I look at it just like I'm seeing right now, I see I have 10 and 22, so 10 over 22, and then I have 11 over 20. Okay, 10 over 22 and 11 over 20. And the problem is that this is not correct, or in other words, these are not proportional. Okay, but what some of you guys might be seeing is that if I swap those around, if I start with the ones that are diagonal from each other, so for instance 10 over 20, and then the other ones that are diagonal from each other, 11 and 22, this would be proportional, okay, because both of these would simplify down to 1/2. Okay, so in this case, these sides are proportional, except it's not just being reflected one side over the other, it's actually being rotated around, okay? And so this is why we're going to give the theorem, which this is side, angle, side. So I'm going to say side, angle, side, similarity theorem. And then I need to be careful about how I write my similarity statement, or in other words, when I go to say which triangles are similar. So let's start with the first triangle here. We'll say triangle, and it doesn't matter how we order this one, TWZ for instance, the triangle on the left. And we're going to say that's similar to, so I'll go ahead and draw that squiggly line to remind me that that is the similarity symbol. And I'm going to say that's similar to triangle. And remember, I don't want to go and say XWY, as if it was being reflected, but I want to go in the opposite order. I want to go YWX because it is as if it's being rotated around. So that Y and T are corresponding, WW are corresponding, and then same thing with Z and X. Okay, and this would be my final answer here. Okay, so on these problems, the difficult part, in my opinion, is not going to be setting up proportions because you guys know how to do that. The difficult part is being able to see which points are corresponding. And that's why it's so important to pay attention to which sides are going to be proportional. Okay? All right, which leads us to our last example here, example 4. If you'd like to, you can pause your video and sketch this. And we're going to use we're going to give the similarity statement here, and then we're going to solve for x. Okay? So if I'm looking at these two triangles here, I need to make sure I pay attention to which triangles I'm referring to, because I see I have technically three in this picture. I have this small one on the left, I have another one on the right, and then notice the entire shape as a whole, the entire diagram is one big triangle as well. Okay, so if I'm looking at all the information that I have, I'm given some different side lengths here, and notice I have one of the angles, angle H, is congruent to angle D. So that's one pair of angles that I have. And then the only other thing that I have is that angle G is going to be congruent basically to itself, because I don't see any other angles in this picture that have two arcs on them. So if that is the case, if we're trying to figure out which two triangles are the ones that are congruent, well, I notice one of those triangles that has two angles that I'm given is the one on the left, triangle GDH. Okay? And then I notice the other triangle with two angles in it would be the large triangle GHJ here. Okay, so I need to make sure I line these up correctly. So let's write our similarity statement. We're going to say triangle GDH, the one on the left, because remember, it doesn't matter how we name the first one. And we're going to say that's similar to triangle, and now this is important how we name the second one. So if I start with G over here, remember we said G is going to be congruent to itself because that's the only other angle that has two arcs on it. So G matches up with G, or itself. Okay, and we're looking at the big triangle, so we start with G. Next is D here, and remember we said D and H are going to be corresponding, so I'll say GH, so GH right here. And then the last side, or the last point in this big triangle is going to be J. So J is actually going to correspond to H. And so this is where it gets confusing, is I have two different shapes that are overlapping and different points kind of correspond to each other. And so here's what I'm going to do, is if it helps, I'm going to draw these out separately so that they look the exact same. So what I'm going to do is I'm going to draw GHJ, and I'm going to leave this as is. I'm going to leave it oriented the same way that it is. And so with GHJ, I'm given 7 here, and I'm given 10. Okay, that's simple enough, right? I'm just given two different side lengths. With GDH, I want to kind of rotate this around or spin this around so that it looks the exact same. So basically, I'm going to take G and move that up here and kind of rotate it around. And then H will come down here so that when I sketch this, we'll have G, D, and H. Okay, G, D, and H. And notice how now it looks like all of these sides are corresponding. I've just taken this shape, or this triangle, and basically reflected it. And so now when I go to write in my side lengths, I know I have GD, which is 2x minus 2. And then HD, or DH, which is 2x plus 4. And if I gave you this problem is a lot simpler, okay? This is where I said the difficult part comes in. We have to be able to know how to swap this triangle around so that they look the exact same. And now I can see which sides are proportional, which sides are going to line up, and I can start to set that up. So I see here, if I'm going to set up my proportion, I can't find the scale factor because GDH doesn't have a side length that is just a number. So I'm just going to take one of those side lengths, 2x minus 2, and we're going to set that over the corresponding side, which if we see from here is going to be 7. And here, if I even want to, I can do this as well to show what angles were congruent to each other, H and D. Okay? Okay, so that's 2x minus 2 over 7, and that's going to equal, and I'm going to do the same thing with the other corresponding side, so 2x plus 4 over the corresponding side, 10. Okay, this is how we set up these proportions, setting the corresponding sides over one another, and now I can cross multiply and solve. So if I cross multiply here, I'm going to have 10 times 2x minus 2. Remember, anytime you have an algebraic expression, I would put that in parentheses to remind yourself to distribute. And that's always going to equal what I get when I multiply the other two here. So that would be 7 times 2x plus 4, again, putting that in parentheses. And now we can distribute and solve. So I distribute here. I have 2x times 10, so 20x minus 20 equals 7 times 2x is 14x plus 4 times 7, which is 28. And now we just need to solve. So we subtract 14x from both sides. Subtract 14x. When I do that, these cancel. I'm left with 6x minus 20 equals 28. Continue here, I add 20 to both sides. Looks like I'm gonna run out of room on my screen here. I'll move this over. So we have 6x equals 28 plus 20, which is 48. And then divide by 6 here, and I'll just go ahead and write my answer over to the side, way over here. I get x equals 48 divided by 6, which is 8. Okay, and so this is my final answer here. So like I said, if it helps, I would draw the triangles to the side and reorient them the way that you need to, so rotate them around, reflect them around, whatever, so that it's easier to see which points are corresponding. And that's why we always pay attention to the similarity statement here, because this tells us which points match up with which, okay? All right, so that is the notes for today. The assignment that goes with this is 8.2 homework, similar triangles. As always, if you guys have any questions, feel free to let me know, all right? Thanks, guys.